Can we start? Okay. Okay, good morning, good evening, everybody. Can we start? So we have this second session of the discussion here. Okay. So first of all, I think I will. Okay, good morning, good evening, everybody. Can we start? Some of the common concerns that many of you second put through in the session discussion forum. The discussion here. There was kind of confusion. First of all, I regarding the particle I will. Okay, good morning, good evening, everybody. Can we start? The common so we many of you second put through in the session discussion forum. The discussion here. The questions that are forward in the kind of confusion doc regarding the particle I will. Okay, good morning, good evening, everybody. Can we start? The common so we many of you second put through in the discussion. So the discussion here. Questions that are like in the kind of confusion doc regarding the particle. I basically okay, good morning, good evening, everybody. Can we start? The common so we many of you second put through in the discussion. So the discussion here. Questions that are like in so we can have the slide. First of all, regarding the particle. I basically so good evening, everybody. Can we start? When we common so we many of you second it always put through in the discussion. So the discussion here. Questions that are so we can have the slide. First of all, regarding the particle. I basically so happen good evening, everybody. Can we start? When we common so we many of you second it always put through in the discussion. So the discussion here. Questions that are so we can have the slide. First of all, regarding the particle. I basically so happen good evening, everybody. Can we start? When we common so we know have electron it always through in the discussion. So the discussion here. Questions that are so we can have the slide. First of all, so that is regarding the particle. I basically so happen good evening, everybody. Can we start? When we common so we know have electron it always through in the discussion. So electron interactions. So an electron which is interacting with say not other particle but an electric field, electromagnetic field, that is also understood as interaction of particle through a photon, with a photon in the quantum picture. Okay. So what we do is to actually look at the electromagnetic field as a quantized collection of photons. This is a collection of photons now. Now this means that when we talk about the particle-particle interactions, we can now think about these photons coming from or emitted by one of the electrons interacting with another electron or another charged particle. But before actually I will show you how that is depicted. In fact, some of this we have already shown in the lecture notes. But what we will do here is to go through kind of systematically from the basic points, basic interaction of a particle with the electromagnetic field, and then later on I'll show you how that is taken as the interaction between charged particles or between two particles, quarks or leptons, etc. Okay. So this I don't see the slides. Hopefully you can see the slides. This yeah, so that if you go to the next slide, the second slide, so we can see that the photons can be emitted by an electron, or it can be actually be absorbed by an electron, the second one that we have, or an electron and an electron that come out. Okay, No, the previous slide itself. Okay, I will tell you when to change the slide later. So this electron and a positron can come together and a photon can be created, or from a photon, which means the electromagnetic field, electron and positron pairs can be created. So you can see that in any of these, the charge is conserved, electric charge is conserved. So for example, the so let us go to the second slide, the previous one, the electromagnetic field itself. Okay, so there we have an electron emitting a photon and going as an electron itself. So the electric charge is conserved. In the case of electron and positron annihilation to become a photon, there also the electric charge is conserved because electron has a minus one charge, positron has plus one charge, and then they come together and then it is the same. I mean, it is total charge is 0 at the vertex, and then later on when the photon is created, that also has 0 electric charge. Similarly, when photon is created, but we have not seen experimentally an electron and some other positively charged particle coming out. Electric charge is conserved when we consider, say, electron and a muon. But this does not happen. We don't see that. This is what we call different flavors of the lepton. Say, electron is one type of flavor, muon is another flavor. So different flavors are not mixed in these reactions. Similarly for the quarks also. Quarks also have electric charge. They interact with electromagnetic field. We see it as interaction of the quarks with photons. Now, photon interactions do not mix up the flavors. Say, for example, a U quark and a D quark does not interact together with a photon. But it is always a U quark emitting a photon and then going as a U quark, or a U quark and an anti-U quark coming together and then emitting a photon, etc. This is the same with weak interactions as well. In the strong interaction case also, but in the strong interaction case, leptons do not take part. There is no electron or muon interacting with gluons. Okay, the photon is replaced by the gluon, right? And so if we go to slide 3, there you can actually see that the photon is now replaced by the gluon, and when it comes to the strong interactions. So the picture I will share these slides with all of you later. So, and then we can discuss over the discussion forum as well if there are further questions or confusions. But basically, in any of these reactions, the U quark, when it comes to a U quark, it will always be a U type quark that will come to this thing. Okay. When it comes to lepton, it will be electron and it cannot mix with a muon type this thing. In the case of weak interaction, the particle that is exchanged, like that is quantized, that is the representing the field, are different, two different types. One is a neutral particle like the photon, which is called the Z boson. The other is W boson. The W boson is charged, electrically charged. This we had seen when we looked at the beta decay, for example. In the beta decay, you have a W which is exchanged between these quarks and the leptons. So there is a D quark actually converting itself into a U quark, and a W is emitted. their electric charge is conserved again when we consider the charge of d quark, u quark, and the w together. Okay, so this is fine. So there are various different these things that are possible. It can also actually club with the W can also club with or can actually interact with the leptons, the electron, and the neutrino. There always when W is interacting with a lepton, there is always a neutrino associated with that. Again, it is not the neutrino along with the electron which is going to come out, it is a anti-neutrino. So these are some subtleties. But if you don't understand all of it, maybe in some of the later lectures we are going to discuss this a little bit more, or in the discussion forums we can discuss more. But basically, whenever we talk about particle interactions in the quantum picture, it is like particle interacting with the corresponding field, force field, whether it is electromagnetic interaction or strong interaction or weak interaction, the corresponding field will come, and then through that quantum of these fields, it will interact with other particles. So there is no direct interaction of particle and particle like electron and electron or quark and quark that we have in our present theoretical framework. Okay, so this is how we understand it. There are difficulties if we consider the direct interaction of particles without the mediation. So theoretically there are difficulties, and then whereas when we consider it in this fashion, there is no difficulty in mathematically formulating the interactions, and it has been quite successfully understood through this kind of framework and mechanism. So that's why we say that we have always a kind of an interaction like this thing through this mediation of the photon when we consider the electromagnetic interaction of two charged particles. Yes. So if we consider the different processes as we go through, say for example, positron and electron annihilation and creation of two other pairs of charged particles, say muon or anti-muon or quark pairs, etc. This is always understood through first interaction of electron and positron, then the photons come out or photons are created, and then these photons are they create pairs of other charged particles. Similarly for the strong interactions. In the case of strong interactions, so we can go to the next slide where we actually show the strong interactions. Okay, so the strong interactions, we have quark interacting with each other and then creating a gluon and field, and then the gluons convert into again quarks. But then in this strong interactions, we will never have leptons, electrons, or other particles. Whereas in the case of weak interactions, whereas in the case of weak interactions, we have this W boson or Z boson, which can actually go into this leptons or the quarks, etc. Okay. So going to the next slide, we have, I think that is what we have said in the next slide. And basically this is the kind of thing that we have kind of discussed in the but we wanted the basic interaction in the lectures that we have not elaborated, but these are the things that we wanted to kind of discuss and then try to understand. Okay. So this is one of the things that I wanted to discuss in detail with you. Okay. Now, what we can do, if I will first of all, I will share these slides, and then you can we can discuss it in the discussion forum. Okay, and then I will tell you if anything more at the moment can be done. See, some of the details it is difficult to discuss because it requires certain elaborate discussion of the mathematical framework, etc. But nevertheless, we will try to discuss as much as possible in the discussion forum. Okay, so you post your problems or responses in that, and then we can actually I will tell you either references or how to deal with that if it is quickly understood by within whatever whatever the quantum mechanics or the things that we have been learning is allow you to that we will do. The rest of it I will tell you that you can look at the detailed references later. Okay. So now let me go through some of the questions which you have already posted in the Google Docs. Okay. So one question was to actually discuss the optical model of the nuclear interactions. See again, when we discussed the nuclear interactions, it was kind of brief and sketchy. It's because there are different topics that we wanted to cover in this thing, and then it is not really our focus. I mean, it was not really one of the focus that we wanted to have, the nuclear interactions. So that's why we had not gone through the details of it. So optical model for nuclear interactions is basically to understand the nuclear scatterings. Okay. Not really going through the detailed interaction at the nucleon level, but taking a kind of overall phenomenological aspects and then putting it into a kind of an effective model, similar to saying a liquid drop model, some kind of a cloud of some gas cloud going kind of a thing that we can think about, where the scattering takes place at the nucleon level, what type of things will be absorbed and what type of things will not will be transmitted and scattered, etc. will be dealt with in the optical model. That is it. But we will not go into the details. What I will do is to actually give you some reference, and we can see some of you. This is not general. Is not going to be a of general interest, so I will not go into the detailed discussions. But what we can do, if there are some specific discussions for some of you, that we can take up later. Okay. The another question was the stability of the isotopes. So should we take N by Z ratio or binding energy per nucleon? Which one is the better one? It's always the binding energy. The binding energy dictates other things. The binding energy of the nucleon binding energy per nucleon of the nucleus will decide kind of the stability of the particle. The abundance, on the other hand, will also depend on other environmental factors as well. But the stability will be directly related to the binding energy, because every system wants to achieve the minimum energy configuration. So the larger the binding energy, the smaller the energy of the system for a particular number of nucleons in it. Okay. So then another question is on how the created electron. So we created electron by gamma ray do they behave like original one? Original one, I think when what is meant is like the electrons which are already present in the atoms, say for example. Yes, they are. So these ones, that whatever we are talking about, that we talked about in the beginning, that the particles which are created, electron pair, electron positron pair, quark pair, or muon pair, etc., they are all the same in the sense that they are, these electrons are the electrons. Electrons have the properties of the electrons which are there in the atoms. It's the same kind of particle. That is why we call it the electron. Okay, so they don't have any distinction. So if you are given two different electrons, one taken from an atom which was existing there already, and the other one is created in this fashion, then then you can actually, you will not be able to see any difference between these two. Okay. So then there is another question which was already there. How can we know more about the universe through elementary particles? This is an interesting question, and it actually requires a lot of time to discuss. But basically, the short answer is that basically the dynamics of the elementary particles actually had a lot of impact on the evolution of the universe, especially the early universe, evolution of the early universe. So, for example, the nucleosynthesis, Big Bang nucleosynthesis, if you have heard about, if you have not heard about it, is basically the creation of the formation of the small light nuclei, the nuclei of helium or deuterium or the lithium, etc., in the early universe was dictated by the the dynamics that we have been discussing in the nuclear physics part here. So that is the binding energy of when the proton and neutron coming together, etc. All this physics goes in there. So it is extremely important to understand the nuclear physics, to understand the nucleosynthesis of the early universe, and that in turn is very crucial. How many of the protons and neutrons came together, and how many of the protons were left out as hydrogen nucleus, or what is the abundance of deuterium, what is the abundance of the helium, what is the abundance of lithium, etc. in the early universe. When I talk about early universe, this is in the first 10 to 100 to 200 seconds of the evolution of the universe, the first 3 minutes that as we talk about. So that's when all this matter was created in the universe. Everything else is created from that. So how much of this was there earlier is very crucial, and nuclear physics dictates the dynamics at that time. So it is very important. Even before that, earlier times, okay, when the universe was younger than that, at a higher energies or higher temperatures, the dynamics that we are talking about in particle physics, elementary particle interaction, are crucial and important. And so therefore, in the one sentence, it is extremely important to understand the elementary particle dynamics to understand the evolution of the early universe. And the evolution of the early universe certainly dictates how the universe has actually evolved further. Okay, what we will do, maybe when we come to the next live session, by that time we will be in a better position to actually discuss this. So I will see if we can actually give you a little more details of this at that time. There are very interesting things that is going on there in that time, and which we have not yet understood, and then which are going to actually, which are in the current realm of the particle physics research and cosmological research. Okay, so we'll come to that in detail for later. So for the another question was this: what is the electric charge radius of proton, and how does it differ? The proton is kind of small, slightly smaller than 1 Fermi, say 0.9 or some such number within the uncertainties. Okay, so 0.9, let us say. This is well understood through experiments, scattering experiments with electrons, and the electron basically. And there are also these experiments are going on to actually measure it more and more accurately, but the present understanding and the thing is at 0.87 Fermi, I think. Yeah. But when it comes to gluonic charge, I think what the question is that when we talk about the strong interactions and the gluon or the strong charge kind of thing, and what about that, the strong interaction? In this case, it is slightly more difficult experimentally to probe it. Okay, this radius is basically the radius of the proton, the size of the proton. When we discussed earlier the size of the nucleus, what is the size of the nucleus, etc. The same thing can be actually extended to this here. But scattering experiments determine the strong interaction distribution or the gluon's influence, how much that extends in the proton. Because we don't really have isolated strongly charged particle. All the particles in the that we know of are all neutral in terms of the strong charge, not the electric charge, but the strong charge. So, for example, the quark cannot actually be free and then moving. We have not seen that. We cannot. There are theoretical reasons that we have kind of found why it could not be going out, which is called a confinement. They are always in pairs, either as mesons or baryons. This we have discussed that what is a baryon and what is a meson. So they are the bound states of these quarks. So we can see only the bound states of these things. So the scattering with the bound states will not really give you enough information about what is the strong charge distribution in a way. Okay, so it's more difficult, but we can assume that it is the same more or less as the electric charge distribution for all practical purposes in a way. So what is the magnetic moment of then they cannot really have any magnetic moment, but quantum field theory or quantum electrodynamics allows to have what is called the quantum interaction. Say we cannot talk about any elementary particle as isolated in a way. There is, in the quantum picture, there is always, when we talk about an electron, there is always an emission and absorption of the photons associated with that. Similarly, for the neutrino also, there is this, it cannot emit the photon directly, but it can emit the weak interaction part, the W boson, for example, emit and absorb. We cannot see the W coming out, but we can actually emit and absorb. Quantum mechanically, it is allowed to violate the energy within a short time. Okay, so because of the uncertainty principle. So there what happens is this is called the virtual particles. Okay, don't worry about it if you get confused with what is virtual. So these are called the quantum effects, and these quantum effects can actually generate some small magnetic moment. So again, I think we won't be able to go into the details of this because we need to know more about the theoretical framework there. So are neutrinos their own antiparticles? How do they get their mass? Yes, they are their own antiparticles, and then they get their mass through certain mechanisms that again we will not be able to discuss here. It is the only thing that I can tell you is that this is slightly different from the way that electrons get their mass. Okay, so that's a different type of these things. For those of you who have heard about it, there is something called seesaw mechanism, which is the most popular theoretical mechanism that many people believe is the origin of the neutrino mass. But we have not established that yet. And if we are talking about, so there are again, when we talk about the antiparticles, there again, if there are two different type of fermions that we can think about. One is the Dirac particle, Dirac fermions. The other is a Majorana fermion. These Dirac fermions are like electrons. The particles and antiparticles are different, even if they are neutral, like the neutrinos are different from antineutrinos, whereas Majorana particles are their own antiparticles. So again, we'll not go into the details. I will just talk about just saying that there are these different types. So it depends when we talk about neutrinos, whether they are on their own antiparticle or not. It depends. Okay, just one more thing I can tell you. We discussed the double beta decay. When we discuss the beta decay, we also discuss the double beta decay. So there is something called neutrino-less double beta decay, which means that two electrons come out but without the associated neutrinos. So these neutrinos usually accompany any beta decay. So if it is a double beta decay, normal double beta decay, then there are two electrons and two neutrinos coming out. But in the neutrino-less double beta decay, these two neutrinos do not come out. What happens is, it is possible that the neutrinos which are supposed to come out, there are two of them, and they are also their own antiparticles. So one can get annihilated by the other one. So this is not going to happen if they are Dirac neutrinos. If it is Majorana particle, then it is. So this is where one experiment which can actually clearly distinguish whether the neutrino is a Dirac type neutrino particle or not. But we have not really neutrino so far. So we don't know yet. Quark flavor conversion is that valid in the quark gluon plasma? Yes, quark flavor conservation is something which we have seen everywhere. So far, we have not seen any flavor violation. Okay, so okay. So far, that is so. Then I don't want to go into more details of the flavor violation in the quark sector, which will take us away from the topics that we are supposed to, we can cover in this thing. Okay, it need again more detailed analysis, etc. How does it affect the magnetic field again? Magnetic field is, as you know, wherever it is, if there is a charged particles, then you can actually think about the magnetic field affecting that. Okay, so that is how it goes. So quarks, if you have quarks, then it will affect the it can be affected by the magnetic field. But the point is, in the quark, gluon, plasma, etc., there's a strong force already, and the strong force wins over the electromagnetic force, and so in the elementary particle, when we have two quarks interacting with each other, the gravity is there, but it is completely negligible compared to the electromagnetic. Similarly, magnetic field or electromagnetic interactions are negligible compared to the situations. But yes, they can. Okay, so these are some of the questions that we have had. There are some late questions which I did not really have time to look at, but maybe we can actually look at it in the, and then I can try to actually answer in the discussion forum. So let me look at the chat in the live session YouTube chat thing. Okay, so and then see if I can take up some of these. Why do particles with the same composition, say UUD, have different mass? Well, I think this we have said many different times. Like, it is basically they interact with each other. It's not that take three balls and put them together, they weigh the same. Okay. And so here we are not taking two completely non-interacting objects. They are interacting objects, and interaction is energy. So the Hamiltonian, when we talk about the Hamiltonian, basically that is the energy operator in the quantum picture. So that is why we talk about the Hamiltonian. I think at some point there was some discussion, somebody had asked a question why we talk about Hamiltonian. It's because the Hamiltonian is the energy operator, and then that is one way to understand the dynamics. What is the Hamiltonian, and then what are the effects on different physical systems of this thing, etc. Okay. So when we look at it, there are interaction terms. Like in hydrogen atom, we have energy is of the system is affected by fact whether there is LS coupling or not, or what is the LS coupling, or whether we have some other electric field or some other field there. The energy of the system will change. So here, when we talk about the three quarks, they are interacting strongly, and these interactions can actually have different ways of manifesting, and that is one way to understand. It's not always that the UUD quark will interact in this particular fashion and give you this one, only the proton. They can interact and give you a different system, stable or slightly unstable, but kind of a quasi-stable, a particle-like thing which can actually decay immediately within a short time. So many of these resonances that we are talking about, the baryons, etc., they are not stable like proton, or not even like neutron, as much many of them. So they are quasi, not really quasi, I mean, they are particles well as understood by their mass, by their spin, by their charge, etc. But they cannot stay like in for a long time. They decay immediately. So the delta, for example, baryon, is not stable like proton. They are created and then they are being seen in different nuclear or different reactions, and they can actually be well established by their characteristics like the mass, etc., that I told you. So now, yeah, I think that is by and large the thing is, and their properties like mass, charge or the spin, etc., is understood through the decayed particle and the energy of the reactions which are involved, etc. They cannot actually be, I mean, there are different ways of understanding this. I think we will not elaborate on that. It is basically, you can keep the question in mind, and then as we go further, not only in this course, later on when we discuss, when you discuss the, or when you learn particle physics course in details, you will understand it better. Okay, but short answer is that they can form different kind of bound states, and then interactions can actually give more mass or less mass. Okay, so another question, we can find electric force on interaction between atoms or between nucleons, then we have no observable electric effect on non-integral quarks. Ram, I have not completely understood the question. So maybe if you are talking about okay, I think you can repose that question or then put it in the discussion forum, and then we can try to understand it, because if I say something else, then that may not be what you wanted to know. What are the form factors and why do we need them? Yeah, form factors we did talk about at various different reactions. Okay, the short answer, part of it we have already discussed in the lectures, is that if you take a proton and electron scattering on it, if it is a point particle, then we don't really have any form factor kind of a thing that comes in. The form factor will be basically some function which will depend on the momentum exchange between the scattering, this electron and the proton. Okay, Q that we had denoted in the lectures. So this Q is the momentum difference, or the exchange of the momentum between the electron and the proton. And the reaction will depend on the Q square. Okay, so that will happen, I mean, over and above, or beyond just the charge. Usually, if it is point particle, then you think about the Coulomb interaction. That's it. But beyond that, if there are things that some functional dependence on this exchange of this one, okay, so that is what we call the form factor. Okay, and these form factors are required to understand how the interaction happens between the structure of the proton and the electron. So if the proton is point particle, then there won't be any kind of such momentum dependent factors. But if it has some structure, if it has further substructures, if they are made of further smaller particles like quarks, then we will have this momentum dependence beyond what is there in the Coulomb interaction. Okay. Again, I think if the specific questions regarding this further, then we can actually look at it later. For momentum calculation, at least one problem. Okay, we will try to do more problems definitely, but what you can do, rather than say that okay, let us do that, so you can suggest, if you have done something, you just post that or send me by email. In some cases where you have actually tried to do some problem and then you are not getting the right answer, or you are not able to do that, you write it down on a piece of paper, take a snapshot of that, and then post it or send it to me by email. I will be able to, or one of us, Alolika or Srimanti, one of us, our team will be able to take it up, look at it, and then discuss that with you. Okay, so it will be, that is how we will go. I mean, I can understand that many of these concepts are new, and then it will take time for you to actually absorb and understand it. So we are trying to go slow, but if some of you find difficulties, then the way to deal with it is actually try to write down the details of this one. Say that this I tried, this is how it goes. If I tried, say for example, taking the dot product between 4 vector, and then I'm not able to get this, or I'm getting this, is it correct? All these things you can take a snapshot and send it. If you don't want to post it in the discussion forum, that's fine. You can send it to me by email. Okay. If the email is not available to you, I will post it again. Okay. That's what we will do. So those details are difficult to take up in this kind of session. So I'm going ahead without looking at it. Again, explain eightfold way. I mean, it will take, there are these lecture videos, you look at it, but beyond that, it will take long time to discuss that here. Okay. So this session is basically to sort out the small problems that you have in the discussions that we have already gone through, not discussing a new topic or discussing a particular topic elaborately in that way. Okay. For that, what we can do is to actually use the regular discussion forum. All right. Okay. What are questions? Then recently come out chat, why quarks do not exist isolated? It's because we don't know yet actually. Okay, the question is why quarks do not exist in an isolated fashion. They are always combined with other quarks or other anti-quarks. Okay, it's not completely understood. Theoretically, what we call as a confinement. So confinement of the quarks is something which has not been understood completely. Okay, why exactly that happens? But this is put in as an ingredient. It is similar somewhat, saying that we know that the electric charge is conserved in every observed physical phenomena, but we don't know what exactly is the reason behind that. Okay, so this is kind of an ingredient that we put in from our observation, and we hope that one day later on, maybe when you all grow up and then study this and in detail, we will be able to find that. Okay. Is it possible to find a combination of quarks that are not completely color neutral? No. So far, we have not seen any bound state which is not color neutral. And that is why the theoretical framework takes it as one of the ingredients that any bound state, observable bound state, is a color neutral particle state. Okay, so some of you, couple of questions are there on the exams. Yes, we will have MCQ. I mean, it's already, the CET, Kalal had already replied to you saying that we will have questions which are similar to that of the assignments. There could be multiple choice questions, multiple answer it could be, or a single answer, or it could be a short answer question where you will have no choice given, but you will be asked to write either a numerical this one, or mostly it is numerical if it is a short answer one. And it could also be some words, but I think we will try to avoid any such confusion or ambiguity. But basically, the nature of the questions will be very similar to the assignment type of this thing. The type of the questions will be similar to that thing. Okay. For momentum calculation, one problem. Okay, what are the form factors that we looked at? Let me see if quickly if there is any. So can you suggest some books which I will look at? What are the difference between neutrino and anti-neutrino? Most antiparticles have their charge. Yeah, here in the case of neutrinos, yes, that is another question. What neutrino is charge neutral, electrical charge is 0, and there is no strong charge, but it has a weak charge. So it is basically the weak interaction that distinguishes the neutrino from its antiparticle. Okay, it is there is no electromagnetic interaction there. What is the difference between neutrino flowers like E? So yeah, this is another thing we have told, but may not have told it in a detail or emphasized on it. Neutrinos come in 3 different types: electron type, muon type, and tau lepton type. So, okay, associated with the charged leptons, electron, muon, and tau particles. So these are the 3 different flavors. So the electron, the neutrino that is coming out in the beta decay are the electron type neutrino. Experimentally, they can be distinguished by, say, for example, trying to take out or expose these antineutrinos coming out in beta decay and then trying to make them interact with the neutrinos, or sorry, interact with the muons. And these type of experiments will tell us whether they interact with muons or not. So that is where we can actually distinguish experimentally different flavors. If they do not, then they don't really, or the neutrinos that are coming with or associated with the muon, they are seen in the basically the pions decay to muons and antineutrinos, or if it is pi plus, it will go to anti-muons and neutrinos. Muon type neutrinos. They are muon type neutrinos. They will not interact with electrons. Okay? So this can be experimentally distinguished as well. So now we have established experimentally that there are 3 different types of neutrinos. Photon is its own antiparticle, yes, and it means that okay, this is kind of a theoretical this one. When we talk about an antiparticle, there is a way theoretically actually also to go for symmetric transformation of the particular wave function of particle to an antiparticle. Mathematically, we should understand that how that happens, right? So this is well understood, how what type of transformation take a wave function from particle state to an antiparticle state. So there the photon state actually transforms in this fashion, like the same thing you will get even when we do this transformation. Okay, it's particle to antiparticle transformation. Again, I don't want to go into details of what is that transformation, etc. But that's there. Okay, so there is something called charge conjugation. It takes you operations similar to parity transformation, etc. So that will take you from a particle type to antiparticle type. Okay, under that, photon behaves the same. So it is the same. So that is when we call it the particle and antiparticle are the same. Okay. What is the major difference between detectors and proportional counters? Proportional counter is a particular type of detector. So, again, there is a question on eightfold way. Okay, so I think this is the same question. So I think I will refer you to the particular lecture and then tell me if there is any specific question on that. Okay. Okay, I think we can W particle distinguish muon and electron? Yes and no, in the sense that there, if you are talking about distinction, what do we mean by distinguishing? If W interact with electron and muon with the same strength, same fashion, same way, then the answer is yes. There is no distinction that we can make between the interaction of a W and a muon. This is what's called the flavor symmetry, that the W particle interact with electron and muon separately in the same fashion. So that's what they call the flavor symmetry and lepton flavor symmetry. And this is seen to be the same so far. In people are looking for differences. This difference is called the flavor symmetry violation. And it has impact on particle dynamics. Therefore, people are really searching for it. Theoretical frameworks are also trying to see if consistent framework can be made with such kind of a thing compatible with the experiments. So far, answer is no. They don't. It is the same. Okay. Yeah, but it is an important topic that we have been trying to understand experimentally. Okay. Is the photon fundamentally stable, and how do the quarks and gluons carry the spin of the proton? Yeah. Proton is stable. Proton is stable because of baryon number, because otherwise it will violate baryon number violation. So baryon number in any reaction that has proton decay, because the proton is the lightest baryon that we have. Now, how do we get the proton spin from gluon and quark spin? Again, this is a topic of research. It's not just combining these three particles in a way and then see, because we have to understand the interactions. Gluons are not one gluon or two gluon in proton. It is basically the many different sea of gluons, and that gluon can actually have a large contribution apparently. That is our present understanding, that gluons also contribute largely to the proton spin. I don't think I can tell more than that here, because it goes into quite a lot of details of the quantum chromodynamics, the strong interaction dynamics. But yes, it is fairly understood, but not completely understood, in fact, of how exactly the spin of proton arises from the gluons and quarks. Okay? But it is established that gluons contribute quite a lot. How are the four momentum vectors related to one another? They are not related to. I mean, if you take two different four momenta, they are not necessarily related. But if in a reaction, if you are talking about electron and proton scattering, giving rise to some new set of particles, then the sum of the initial momentum will be the same as the sum of the final momentum. Okay, so this is basically the energy conservation, because one component of this four momentum is energy, and the final one is also the if you add all the four momenta, then you will get the energy and momentum, three momentum of all the particles combined. So that has to be conserved. So that kind of relations exist, but otherwise not. Okay, I think we will kind of wind up here and then take further questions and then discussion in the discussion forum and maybe in the next live session. Okay, thank you all.